Hi, I'm Miss Hearn. Let's get started. Okay, so it says, for the function given below, find a formula for the Riemann sum obtained by dividing the interval AB into n equal subintervals and using the right-hand endpoint for each c sub k. Then take a limit of this sum as n approaches infinity to calculate the area under the curve over AB. Okay, so for the first part, which is actually finding the Riemann sum, what you want for your Riemann sum is S sub p equals the sum of the f of c sub k times delta x sub k, and that's k equals 1 to n. And we'll go over what each piece of this means, but you want to start with identifying a, b, n, delta x sub k, and then you're going to partition the interval using delta x sub k. So you're going to identify your partition. The partition itself isn't as important on a Riemann sum as the kth right-hand endpoint in the partition. But I like to write out the partition so that you can relate it back to what we did when we were doing finite numbers. But we're looking for c sub k, and there is a formula for c sub k, which is a plus k times delta x. And then we'll find f of c sub k, and then we'll find the Riemann sum. A is referring to the left-hand endpoint of the interval from 1 to 4, which would be 1. Yes, good. And then B would be 4. Good. Now, n, when we're estimating the area under a curve, n could be however many rectangles we want to use. But in a Riemann sum, n is left as a variable. It can be any quantity. In other words, we're looking for a formula regardless of how many rectangles. And then delta x sub k is the width of the subintervals where we're going to partition the interval 1 to 4 into. So that is always b minus a over n. We're going to use, the reason for the little k here is to say that when we make our partition, it doesn't have to always be the same size rectangle, but in fact, for calculation purposes, it's usually easier to just use the same one. So you can use delta x sub k or just delta x, and that's telling you the size of a subinterval, which in this case would be 4 minus 1 over n, or 3 over n. So we have the length of the whole interval is 3. We're dividing it into n pieces to create the subintervals. We're partitioning the interval from 1 to 4 by adding 3 over n. So at the first endpoint, which is a, we have just the value 1. And then we're going to go 3 over n away from that, so we're going to have 1 plus 3 over n. And then we're going to go another 3 over n away from that, so we're going to have 1 plus 2 times 3 over n. And we're going to keep doing this, and by the time we get to the kth right endpoint, by the way, this would be the right endpoint of that first subinterval between 1 and 1 plus 3 over n. And then the one next to it, 1 plus 2 times 3 over n, that would be the right endpoint interval here between these two values. And then by the time we get to the kth subinterval, we have 1 plus k times 3 over n. And then if you were to keep going all the way to the nth subinterval, you'd have 1 plus n times 3 over n, which notice that's 1 plus 3, which is 4. So you have spanned all the way from 1 to 4, and you've created this partition, and each piece is 3 over n wide. Okay, you don't actually, this step here is optional, but the only thing you really need from this partition is this. This is the right endpoint of the kth subinterval, which we call c sub k, equals a plus k delta x. That's what we have. 1 was a plus k times, and delta x is 3 over n. This is the x value that we're using to find the height of the rectangle, right? But to find the height of the rectangle, we have to plug into the function. So plugging into f, 1 plus 3k x equals 2x. So we're going to double that, 2 plus, instead of x, plus k over n. And we just found the height of the kth rectangle, which is why you see in the formula for the Riemann sum, the sum k equals 1 to n, you see the area of a rectangle. You multiply its base times its height. So we're going to have this 2 plus 6k over n times 3 over n. So we have to work this out a bit. So the first thing usually is to distribute through the parentheses. So we have the sum k equals 1 to n of 6 over n plus, okay, so then now we're going to split this up. We know that we can break the sum into two sums. Sum k equals 1 to n of 6 over n plus the sum k equals 1 to n of 18k over n squared. And actually, 18 over n squared is a constant. It's a coefficient of k, which we can factor out front of the summation. 18 over n times the sum k equals 1 to n of k. That'll make it easier to see what we need to do using our formulas for summation. The formulas for summation that we would need here is the sum k equals 1 to n of a constant c. You just multiply c times n. And the sum k equals 1 to n of k turns out to be n times n plus 1 over 2. So we're going to use those two formulas. So we have 6 over n is a constant. So we just multiply it by n to get the total. 6 over n times n. Plus, over here, we have 18 over n times. Instead of k equals 1 to n of k, we write n times n plus 1 over 2. So 6 over n times n is just 6. And then 18 over n, the n is going to cancel with the n in the numerator. So, and then the 2 is going to go into 18 9 times. So we're going to have 6 plus 9 times. Oops, I forgot. There was supposed to be an n squared here, not an n. My bad. All right, so one of the n's cancels. So we still have an n in the denominator, and we have 9 times n plus 1 in the numerator. There's not one particular right way to write this, but I'm going to just go ahead and I think what they do in your book is they divide it out. So this is going to be 9n plus 9, and we're dividing each part by n. So you're going to get 9 plus 9 over n. So your result is 15 plus 9 over n. That's just the first part of the problem. This is the Riemann sum, S sub p. So the second part is asking us to take the limit as n goes to infinity. In other words, as the number of rectangles increases without bound, what is the area going to turn out to be? What is it approaching? The limit as n goes to infinity of 15 is just 15, and the limit as n goes to infinity of 9 over n is 0. So the total is 15.
I hope you found this video useful. If you did, please remember to like it.